Hello and welcome to this short presentation on parameter estimation using MATLAB built-in solver fminunc or fmin unconstrained optimization. We'll begin with a background. Why do we need parameter estimation? We'll move on to an example looking at the substrate concentration profile in a bioreactor. And then we'll move on to how to solve this problem using MATLAB code. So why do we need parameter estimation? Dynamic models don't usually align with experimental data because of several factors, including limiting assumptions in the model, noise in the measurement and measurement delay. And if we're considering kinetic parameters, catalyst manufacturers are always innovating, and sometimes these parameters are not available to public domain. Although this is not an exhaustive list, these factors lead to a mismatch between the numerical model and experimental data. Let's look at an example. A numerical model has been developed for enzymatic conversion of a substrate S to a product P in a batch bioreactor. The rate of conversion in the bioreactor is described by the following equation. The reactor is volume 0.1 L containing 10 mg of enzyme, which corresponds to Me, and the initial concentration of the substrate is 2 moles per liter. Vr is the volume of the reactor. Vm, Km, and Ki to the power minus 1 are parameters to be estimated, and S is the concentration. We're also given some experimental data, which is sampled at different times, going from 0 to 330 minutes. We also have a graphical representation of this experimental data. The blue circles correspond to the concentration at different time points. So let's go into MATLAB and see how we can solve this. Whenever using the solver fminunc, it's important to consider the end or the goal in sight. Fminunc requires a function, an objective function, and initial condition. We can read more about it in the documentation in the top right corner, or typing or highlighting and pressing F1. So I'll leave that to you to do some further reading. This is how I would solve it, and it's important to highlight that when writing MATLAB code, it can be individual, and there isn't just only one way to solve this. So I'll begin talking through the numerical model, which I've called a substrate. This is a function file to solve this, a function file describing the nonlinear differential equation. We have our known parameters, 10 mg of enzyme, our reactor volume, our unknown parameters as well, Vm, Km, and Ki. And we also have our nonlinear differential equation in line 14. We have our objective function, which we have our initial condition. We have our time span, spanning from 0 to 330. And we also want our numerical model to follow this time span. Line 13 shows our built-in solver. We've created a function handle to call upon this function file here, and it passes the parameter values through the substrate function, and we can obtain a numerical model to solve the nonlinear differential equation. The experimental data at each time point is also given. And then we set up an objective function which looks at the sum of the difference between the numerical model and the measured data squared. Let's look at the whiteboard for a further in-depth analysis. The blue line is our expected numerical model, and the red dots are experimental data. We seek to minimize the difference between the measured and the numerical model, square those values together, square the values and sum them all together. Consequently, we can map the numerical model to the experimental data, and we can make better predictions in the future. This numerical model essentially becomes reality. We set up, then moving on into our solver file, we list our initial guesses, and these can be initial guesses that can be selected randomly, or we can look at the experimental data and guess where these values will typically lie. Over here, I'm just going to go for 1, 1, and 1 for VM, KM, and KI. fval in line 15 gives us the value of those parameters that minimizes the objective function. Line 17 to line 23 gives the user these optimized parameter values, and lines 25 to 30 updates the numerical model with these new parameters. And then line 32 to line 35 gives us a plot of the measured data and the updated parameters in the numerical model. So we hope to see that it fits the model. Let's go ahead and run it and see what happens. Okay, so we see that the numerical model, which is the red line, does not give us a good fit of the experimental data. We also see that the parameters given to the user are not very adequate. This behavior happens because as the function is non-linear in nature, it has many local minima. As a consequence, the function, when it tries to solve it, gets stuck in these local minima, and it does not solve it adequately. So to overcome this obstacle, we can change the initial guess to get a better result. So I'm going to change this VM to something drastic, something like 500, and you can vary these to see and iterate your way to get a better result. So when we change this to 500, we can see that our fval is 7.5522 times 10 to the minus 4. But how do we know that this is the best guess? We continue with the trial and error approach and manipulate these initial guesses to see if we can change this any further. Let's try 250. We can see our fval now is 1.1298 times 10 to the minus 4 in our workspace here. This also gives a great fit. We see that our fval for a VM equal to 250 is a lower value than 500. So this is a better estimation than 500. Let's see if we go even lower. Let's try 150. We see that our fval is a value that is greater than at 250. So we know that the optimum is between 150 and 200. 150 and 250. So let's try 200. Okay, we see that our fval does not give us an adequate fit compared to its predecessors. So let's try 190. This gives a better fit and is a value that is lower than 250. So let's try 210. We can see that we now get the lowest value of our trial and error approach. So we can stop our trial and error method here and be satisfied with these optimized parameter values. We can see that there's an excellent fit between the data points and the numerical model, and this is our final solution in the command window with VM equal to 210, Km equals 0.22, and Ki equal to 0.52. So that's it. That's the solution. Thank you for listening.